Okay, thank you. Thank you very much. So hello, everyone. I'm Yu from University of Illinois. So today I would like to introduce our work, effective seed-guided topic discovery by integrating multiple types of contexts. This is a joint work by researchers from the data mining group at UIUC. So let me start from the introduction part. So we are studying the topic discovery task in this paper, which aims to automatically discover informative and coherent topics from massive text corpora. It has lots of applications. For example, it can help users efficiently digest a large collection of documents by, say, drawing a word cloud of given all the accepted papers. And then it can also advance downstream applications such as taxonomy construction and document classification. So I put a plate diagram of the unsupervised LDA here, which most of us are quite familiar with. Actually, unsupervised topic models have been the mainstream approach to topic discovery. However, such models tend to retrieve semantically general topics that may not align well with user-specific interests. For example, given a collection of reviews, if a user would like to explore topics of food types, for example, by providing the seeds, noodles, steak, and pizza, then the expected output should be topic indicative terms for each input seed. For example, we need to retrieve ramen and pasta on the noodles, and maybe some other distinctive terms on the steak, and so on. Instead of finding general terms that are relevant to multiple seeds, such as beef, or retrieving topics along other dimensions like good and bad as topics of sentiments. So in this case, the output should really adapt to user-provided seeds. So here comes the formal definition of our seed-guided topic discovery task, where the input consists of a large corpus and a set of user-specified seeds. And the desired output is a set of terms under each seed to form a coherent topic. And such seeds and terms can be either unigrams or phrases extracted from the corpus. So previous studies on seed-guided topic discovery have proposed to use different types of context information so that they can go beyond the bag of words generative assumption of LDA. When they use the context, they can learn the word semantics more accurately and obtain better topic discovery results. However, we argue that each type of context information has its specific advantages and disadvantages. Here we show three major types of context information utilized by previous studies. The first one is skip-gram embeddings based on local context, for example, ±5 words. And we all know that skip-gram embeddings are context-free, so they become less helpful when the word has multiple senses. Actually, a recent study shows that clustering skip-gram embeddings underperforms clustering output representations of BERT or other contextualized language models in unsupervised topic modeling. So since BERT is a better choice, however, that's why many recent studies have switched to pre-trained language model representations. Actually, the transformer architecture can capture longer context signals, and because those PLMs are trained on web-scale corpora, so the learned knowledge can complement context in the input corpus, especially when the corpus is not that large. However, there are also some studies reporting that pre-trained language model representations may generate noticeably bad topics. For example, one study shows that the BERT representations suffer from the curse of dimensionality and do not form clearly separated clusters. Here are the visualization of their results. And another study finds that GPT-2 representations work well only if the output of certain layers is taken. So if you only use the last layer, it may not work. And the Robota-induced topics are consistently of poor quality. So that's the drawbacks of PLMs. And the third common context type are topic indicative documents. The motivation of using this is that skip-gram embeddings and the PLMs, although they are powerful in representation learning, neither of them considers whether the contexts they use are topic indicative. For example, skip-gram embeddings only use the ±X words, regardless of whether they are semantically close to a certain seed. for BERT, even if you have different seeds, so like different seed dimensions, if the input corpus is fixed, the output representation of a certain term in the corpus is always the same. So in this case, to incorporate the seed information, supervised topic models propose to leverage document level training data. For example, we need to know whether the review explains a positive or negative sentiment, or whether it is related to noodles or steak. However, such information relies on massive human annotation, which is not available under the seed-guided setting. And also, the document may be too broad to be viewed as a context unit, because each document can be relevant to multiple topics simultaneously. In our problem setting, we really need to find those very topic discriminative things. So we need to make the text unit more fine-grained. To summarize, each type of context signals has its specific advantages and disadvantages. So if we want to develop an approach purely relying on one type of context information, it may not be robust across different data sets or seed dimensions. So meanwhile, we argue that the three types of context strongly complement each other. For example, BERT has the contextualization power where which skip-gram embeddings are short of. Skip-gram embeddings usually have fewer dimensions than BERT, so that's why they are less prone to the curse of dimensionality. And the topic indicative documents or sentences are not naturally available, but they can be retrieved by applying skip-gram embeddings and preaching language models. So motivated by this, we propose our seed topic mine framework. Here's an overview. It considers the three types of context information mentioned in previous slides. The only difference here is that we use seed-guided text embeddings. In this case, we add one proximity term between the seed and those terms already retrieved under the seed. So in this case, during embedding learning, those terms can concentrate around the seed in the embedding space. So to jointly utilize these three things, we propose an iterative framework, which consists of three stages. During the first stage, topic indicative sentences are not available. So we just use seed-guided text embeddings and the preaching language model representations to find those initially highly ranked terms. This is based on calculating the cosine similarity between each term and each seed in the two embedding spaces, the seed-guided embedding space and the BERT embedding space. And then we multiply these two cosine similarities to get to the initial highly ranked discriminative terms. And based on these terms, we retrieve those topic indicative sentences. This is similar to the pseudo-relevance feedback tree in R. So as we do this, we find two types. It is containing many topic indicative terms, those initially extracted terms from one category and do not contain things from any other categories should be topic indicative. We call such sentences anchor sentences. Second, the neighbor sentences of such anchor sentences should be included as well if they do not contain things from other categories, even if they do not contain those initial terms retrieved for the current category. We show an example here. Suppose sentence 0 is an anchor sentence. We check its plus minus to neighbor sentences. Sentence 1 and sentence 2 may be added as a topic indicative as well. Sentence -1 may contain things from other categories, so it is excluded. And then there's no need to check sentence -2 because it may have diverged to other topics. And finally, we collect all these three signals and we can ensemble the three ranking lists to get to the final list of top ranked terms. And this is an iterative framework. So the retrieved terms can be fed into seed-guided text embedding to learn more like a concentrated, well-separated word clusters. We conduct experiments on two benchmark datasets, New York Times and Yelp. They are collections of news and reviews, respectively, and we compare our methods with 4 baselines. Seeded LDA and anchor corrects are LDA-based, KETM and KATE are embedding-based. We adopt 2 types of evaluation metrics. The NPMI metric evaluates topic coherence. So if we retrieve, say, 20 terms, do they form a coherent topic? This can be automatically calculated using term co-occurrence. And the PI20 and NDCJ20 evaluate term accuracy. We need to check whether the top 20 discovered terms under each seed are discriminatively relevant to the corresponding seed. Of course, this needs human evaluation. So we invite 5 annotators to perform independent annotation, and we do observe a high inter-annotator agreement. Here is our quantitative result. We can find that in terms of term accuracy, PI20 and NDCJ20, seed topic mine consistently outperforms all the baselines. In terms of NPMI, seed topic mine is on par with Kate. It's slightly better on New York Times, but slightly worse on Yelp. Actually, a recent study shows that automatic metrics such as NPMI may not align well with human evaluation. So overall, we still believe our proposed method performs well. And here is a very important ablation study. Because we use 3 types of context information, skip-gram embeddings, BERT, and the topic indicative sentences, what if we ignore one of them? And here is the result. We can see that the full model outperforms all 3 types of, all 3 ablation versions. So the 3 types of contexts all have positive contribution. But more importantly, even for the same data set, the Yelp data set, the contribution of a certain type of context information, like a BERT, varies significantly with the input seed. So the BERT is quite useful for the sentiment dimension, like we need to retrieve things under good and bad. But when it comes to the food type dimension, its contribution is less than skip-gram embeddings. So therefore, this echoes our motivation that it is necessary to integrate them together to make the framework more robust. Finally, some case studies. We show the top 5 terms retrieved by each algorithm in each dataset under each dimension. We can find that those LDA-based methods, they made a lot of mistakes. Kate is significantly better, but it still finds some terms quite general, like also and savory. In contrast, seed topic mine performs much better. So we also have results like for lower ranked terms, like those ranked 15s to 20s, and we also observe similar things. And for more details, you can refer to our paper. So to conclude, we studied the seed-guided topic discovery task by integrating multiple types of contexts, including skip-gram embeddings, pre-trained language model representations, and topic indicative sentences. And we propose an iterative framework to jointly leverage them via an ensemble process for robust topic discovery. On 2 benchmark datasets, we outperform baselines in terms of term coherence and topic coherence and term accuracy. And our code and data and the annotation results are available on the GitHub repo. That's all. Thank you.